Hello, geometry students. Welcome to Unit 9. We are going to be studying polygons, specifically and mostly quadrilaterals, but we're going to start off by talking about all polygons and more specifically their angles today. First, let's start with the definition of what a polygon is. We have a little Freyer model right here. The definition of a polygon is a shape that is two-dimensional, meaning we are not dealing in three-dimensional shapes like this. It is closed, meaning that we could fill the color and it's not going to spill out. This would be an example of a not closed shape. And all of the sides are straight segments. Those segments can go in any way, shape, or fashion, but notice that there's nothing ever curved like a circle or even a piece of a circle right here. Everything is straight segments, closed, and two-dimensional. All of the shapes that you're kind of used to hearing about back in elementary school all pretty much count as polygons, two-dimensional. Some vocabulary, most of which you are kind of familiar with: triangle, quadrilateral, pentagon, hexagon, octagon are pretty commonly known words, but there's a few on here that you might not know. Heptagon, hept is the Greek root for 7, non is the Greek root for 9, deca, just like decade, is 10 years. Decagon is 10 sides. Undecagon, this is 1 and 10 to make 11. Dodecagon is 2 and 12 to, sorry, not 2 and 12, but 2 and 10 to make 12. There's plenty of shapes that you might not know the name for. They all technically have some kind of a name, but particularly those with really large sides, no one expects you to know a name, and no one would know what they were if you did. So we can just call something with 83 sides an 83gon. If we don't know the number of sides, we refer to it as an n-gon, where n is the variable. We use n rather than x because n typically means integers only, and x can have decimals and such. We also have features of polygons such as convex and concave. They have to do with diagonals. A diagonal is a segment that connects two non-consecutive vertices of a polygon. And in a convex shape, those diagonals are all on the inside. And on a concave shape, those diagonals, one of them might be on the outside or exterior of the shape. Let me show you what we mean. Right here on the left, I'm going to draw one diagonal. Notice that it cuts across the middle of the shape. It doesn't go outside the shape at all. These are non-consecutive vertices because consecutive vertices would be like this vertex and this vertex here. Connecting consecutive vertices just creates a side of the shape. So it's connecting two vertices so that it's not a side is what we call a diagonal. The diagonals over on these concave shapes, while one or more of them might stay inside the interior of the shape, at least one of them is going on the outside of the shape. Here's another one that goes across the outside of the shape. This goes across the outside of the shape. Several are going across the outside of the shape. This is another one. We also talk about regularity of a shape, of a polygon. We can have equilateral. Equilateral means sides. Or equiangular, of course this is going to be angles. So equal angles. Regular is both equilateral and equiangular. So that's why we have this Venn diagram where the regular is shaded purple, showing that it is both the blue equilateral and the red equiangular. So let's take a look. Equilateral, right here, we've got all of these sides are the same length, and they're marked as such. But notice that this is a very large obtuse angle, and here's an acute small angle, so this is definitely not a regular pentagon, as we've seen some before. Here's this pretty cool looking star shape. The sides aren't marked, but all of these sides are equal. This is a convex shape, and let's count some sides. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is a convex dodecagon, an equilateral convex dodecagon. On the right, all 6 of these angles are congruent. They're marked as such. So this is an equiangular hexagon, but notice, of course, that the top and bottom are longer than the left and right sides. Here's the regular hexagon by contrast. Here's just a plain old regular rectangle. Don't know why there's a little blue shape around it, but we all know what rectangles look like. Here's all of the equal angles, but obviously the sides are different as compared to a square, which has the equal angles and the equal sides. Moving on to angles. The sum of the interior angles of a triangle is 180 degrees. We know this. The green plus the red plus the blue all adds up to 180. We've used this before. Most of you are familiar with the angles of a quadrilateral adding up to 360. Here's an example with a rectangle, but here's an example with a non-equiangular quadrilateral. 70 degrees, 137, 64 plus 90, they still add up to 360 degrees. This is true with any quadrilateral. We can explain how that works by drawing this diagonal through the middle of a quadrilateral and then looking at the angles in each triangle created. I've marked these angles in this triangle with orange and these angles in this triangle with green. And if we look at the entire angle created right here and right here where the triangles join, I have 1, 2, 3, 4 angles in this quadrilateral that are comprised entirely of those orange and green angles. 2 triangles adding up to a total of 360 degrees. Any polygon has a consistent sum of interior angles no matter what shape it is, as long as the number of sides is equal. Let me show you. Here's a cool little applet. I'll include the link in the modules for you, where we can click and drag any of these orange vertices rather. You can see me clicking and dragging them, and as I move this around, notice that the measurement stays 360 as the sum. Even as I collapse this side to make it concave, now we have this one super obtuse angle. I don't know that that's actually even called obtuse anymore. It's more than 180 degrees, but then these angles are super, super small to compensate. If I add more sides to this shape, let's see, I gotta get the, hold on, sorry. Trying to get this to click. There we go. I'm gonna add more sides. Let's just start with a pentagon. Same thing here, clicking and dragging. Notice that this stays 540 degrees. Stays 540 degrees no matter what I make these individual angles. If I make the shape regular, you can see that it snaps to 108 degrees. And as I make it smaller or bigger, it still sums up to 540 up there at the top. It's a little obscured. As I add sides, you can see that the number for the total is going up as the measurement of each individual angle starts to increase slower and slower and slower, because we are eventually approaching 180 degrees, which then would be a straight line and we wouldn't have a polygon at all. But look at how the shape is becoming more and more like a circle, which is kind of cool. So we could keep going. Eventually, each point is going to get so close to each other that the angles, notice that they're getting very, very close to 180 degrees because it's almost a straight line between each point. But because it's just a little bit less, it forces it to curve around. When we consider how I first broke up that quadrilateral into 2 different triangles to show you how it was 360 degrees in total, we can continue to use that method for any polygon to determine the interior angle sum for any polygon and write a formula. Firstly, thinking about a triangle, the number of sides is 3. The number of triangles inside a triangle is simply 1, and we know that the sum of the interior angles is 180 degrees. When I look at this quadrilateral over here, we already determined earlier that I can draw 1 diagonal in order to create 2 triangles. Each of those triangles is 180 degrees, but times 2, I get a total of 360 degrees for this entire quadrilateral. We can continue this method. Look at the pentagon on the far right. I can draw 2 diagonals from a single vertex in order to break this one up into 1, 2, 3 triangles. 3 triangles times 180 degrees each creates 540 total degrees in this pentagon. Let's continue with the hexagon. I'm going to go again from 1 vertex. I can draw 3 diagonals through the middle, creating 1, 2, 3, 4 triangles. 4 triangles times 180 degrees each creates 720 total degrees. Lastly, with this heptagon, or sometimes it's called a septagon, I can draw 1, 2, 3, 4 diagonals right there for 1, 2, 3, 4, 5 triangles. 5 triangles times 180 degrees each is going to get me a total of 900 degrees there. Notice that we're adding 180 degrees every single time we move forward because we're multiplying by one more triangle that's being formed on the inside. So let's think about what would happen if the number of sides in my polygon was 134. Couldn't possibly draw that, but we can notice enough of a pattern to recognize that the number of triangles that would exist inside of 134 would be 132, which means that to figure out the sum of the degrees, I would simply take 132 triangles times that 180 degrees, and working that out with my calculator, I get 5,760 total degrees in that shape. This lets us fill out a formula. No matter what the number of sides is, you're always subtracting by 2 in order to figure out the number of triangles that we are then multiplying by 180 degrees in order to calculate our total sum of degrees for the interior angles. Here, I just want to summarize that formula for you. S for sum is going to equal 180 times n minus 2, where this is the number of triangles the polygon can be divided into. Sorry, you have to tolerate my terrible handwriting. On the right, I have a box here for the measure of each interior angle in an equiangular polygon. Here's an equiangular polygon, equiangular hexagon to be precise. Because I can calculate that the total sum of degrees for this shape is 180 degrees times 6 minus 2, that's 180 times 4 is 720. I know that all of these add up to 720 degrees total. Well, they all measure the exact same because it's equiangular, which means I have 6 of the same angles adding up to 720. I can go ahead and just divide by 6 to figure out that each individual angle equals 120 degrees. I can extend this for any shape so that my equiangular formula is going to be to take the sum and divide by the number of angles that are in there. If I substitute the full formula for the sum, I have 180 times n minus 2 all divided by n. We're going to return to this formula later because I actually do have a shortcut for this. No need to memorize this, but as always, you can write it down into your summary. Let's do a few examples of how to use these formulas. So here I have this polygon with lots of different angles, and I know they're all going to add up to something. So let's first count how many sides we have. 1, 2, 3, 4, 5, 6, 7 sides. So I'm going to first calculate my sum, which is 180 times 7 minus 2. I get 180 times 5, which then equals 900 total degrees for this shape. I can now move on to all of the individual angles and start adding them up. I have down here in the corner, I'm going to start with my variable z, and I'm going to go around this way. Plus 125 plus 110 plus 95 plus 170 plus 155 plus 115 is all going to add up to that sum we found a moment ago of 900 degrees. All of these values here, you can use a calculator to add them up, sum to 770, and now I can just go ahead and subtract 770 from both sides to find 120. Z is 120 degrees. Here's another example. Here we have a pentagon, so I'm going to use, again, my sum formula is 180 times 5 minus 2. You might start to recognize that you know these values by heart for these more common shapes, and you'll know that pentagon is 540, hexagon is 720. You can also always just keep track of a chart and reference that chart. But I know that the total is 540. I'm going to go ahead and add up my angles, starting with 85, and now I have an algebraic expression, but I can work with that. I have 5x, another 5x, 5x plus 5, and lastly, 5x minus 10, all adding up to that sum we found of 540 degrees. At this point, I just have some algebra to do. First, I'm going to collect my like terms. I have 5x, 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 and 5x for a total of 20x. I see my constants. 85 plus 5 is 90. Minus 10 is 80. And then I still have that 540. I'm going to go ahead and subtract 80 from both sides to get 460. And now I can divide by 20 to get 23. This is just the value of x. This is not the measure of any of the angles. If I was being asked to find the measure of a specific angle, I would need to plug in. Let's say that specific angle right here, I'm being asked to find the value of that. I would need to do 5 times that value of 23 plus 5, which equals 115 plus 5, which gives me a total of 120 degrees. Here's another example. Find the measure of a single angle in an equiangular nonagon. Nonagon, n equals 9. Equiangular, they're all the same. I could go ahead and find the sum by calculating 180 times 9 minus 2, but I can just also go straight ahead to find each angle for the equiangular nonagon by doing this calculation, this same calculation, and dividing straight away by 9. Of course, go ahead and use a calculator. 187 divided by 9, 180 times 7 divided by 9 gets you 140 degrees for each angle. Another example, the sum of the interior angles of a polygon is 2340. I know a formula for that, 180 times n minus 2. How many sides does the polygon have? That's not asking for this value like we usually have been finding out. It's asking for this value, the number of sides. 2340 is the sum. So I'm going to go ahead and plug 2340 in for the sum, and I have some algebra that I need to solve this equation working backwards. My first step needs to be to get rid of this 180 outside of those parentheses. I can either divide both sides by 180 now, or I would need to distribute that 180 and solve that way. I'm going to start out by just dividing by 180 on both sides straight away. I get 13 on the left-hand side, and on the right, I'm just left with n minus 2. I can go ahead and add 2 to both sides to find out that n equals 15. The polygon had 15 sides. If I had gone ahead and distributed, I would have had 2340 equals 180n minus 360. Add 360 to both sides to get 2700 on the left-hand side, left with 180. And now I'm just going to divide by 180 now, and I'm still going to get 15. One more example. The measure of each interior angle in an equiangular polygon is 160. Let's go to that E formula where I have 180 times n minus 2 all divided by n. 160 is going to go in there. 160 equals 180 times n minus 2 divided by n. This is the most complicated algebra in this section. The first thing that we need to do is get rid of this annoying fraction with this division happening right here. We undo division in an algebra equation by multiplying. So I'm going to multiply by that denominator instead of dividing by n. I want to multiply by n. It's going to cancel it on that side. I need to multiply on both sides. I get 160n equals 180 times n minus 2. I need to go ahead and distribute that 180. I still have 160n on the left. On the right, I get 180n. Multiply that 180 by the negative 2 as well. I get negative 360. I'm now going to combine these n terms. I'm going to subtract away the 180n on this side, combine it over onto the left. Leaves me with a negative 20n, which seems weird, but it's negative on both sides. So when I go ahead and divide by that negative 20, my negatives all cancel out, and I'm left with n equals positive 18. My total number of sides in this figure was 18 sides. The exterior angle sum is the last thing I need to go over today. No matter how many sides a polygon has, the sum of the exterior angles will always be exactly 360 degrees. If you take a closer look at this shape right here, notice how when I extend this side and I start going around the shape, I'm going to slowly rotate around the entire side, which means a full rotation, which is 360 degrees. Here I want to show you that applet again, where now I've got the exterior angles marked, and it's showing you how they're always adding up to 360 degrees, even when I grab these vertices and move them around. Doesn't matter which one I grab, or even if the shape is concave, look at how it makes that angle negative, that exterior angle. If I make this shape regular, oops, I lost my touch on this. Go. If I make this shape regular, now as I click in each vertex, you can see that they're still staying the same, but watch what happens as I start to add sides. Remember how the more sides we had, the polygon started to approach the shape of a circle? How many degrees are in a circle, guys? 360 degrees. So look at what happens. Each individual angle is less, but I'm multiplying by a larger number. And look at how we can really start to see how it really is going all the way around the shape. And even if I start with less, look at what happens as I make this shape super tiny. As I collapse it in on itself, look at how it looks like all of these 60-degree angles are just adding up. And I wind up seeing that they all just really add up to a single full rotation all the way across. Okay, example number 6, we're going to use those exterior angles, and we're almost done, I promise. I see this angle marked the same as this one, so this is 50 degrees right there. This is an interior angle, so that's not helpful. I need to figure out this value right there. 180 minus 120 gives me 60 degrees. Here's another interior angle right here. That makes this 70 degrees. Now I see all of my exterior angles marked up. I'm going to start with this x, and I'm going to start adding them up as I go across. X plus 70 plus 50, another 50, another 70, and then lastly, this 60 right here. I know that these all need to add up to 360 degrees. Go ahead and use a calculator. You get 300 for all of those values added up. Subtract 300 from both sides, and I get that x equals 60 degrees right there, and that's my exterior angle. Now we're going to find the number of sides in an equiangular polygon if one exterior angle measures 36 degrees. Well, that sum is 360. When I divide that by the number of sides, I'm going to get that value of a single angle, which in this case is 36. I think you can see that pretty easily, but if I multiply both sides by n, I get 36n, divide by 36, and I find out that my number of sides is 10. You remember that example 5 that we did? Here's the work that we did before. We calculated the number of sides based on each interior angle. But guess what? Because we know the relationship between interior angles and exterior angles is always consistent, we have a bit of a shortcut available to us. This is a terribly drawn shape, but let's pretend that this is an equilateral hexagon, very terribly drawn, of course. We know that each angle in here we can find using that capital E formula. Let's use a little lowercase e out here. I know that the interior angle plus that exterior angle always add up to 180 degrees. And I also know that the exterior angles, when they're all equal, I can multiply them by n to get 360. It's a lot simpler than that formula there. So let's use this to our advantage and redo this example number 5. The measure of each interior angle was 160 degrees. Okay, so I don't know how many sides there are, so this is dot, 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 but I do know that this is 160 degrees. That makes the exterior angle right there 20. I'm just subtracting from 180. I know that 20 times my number of sides gives me 360 degrees because they're all equal, and all I have to do is divide by 20. Look at how much easier it is to get to 18. I highly recommend writing down this formula in addition to this crazy one. That's it. I'm sorry for the extra long video today, guys, but now you're fully ready to go.